Okay, in this video, we're going to go over a problem from Putnam 2003, B6. So this is a technical problem in geometry, but really many of the problems that even have something to do with geometry in Putnam are not necessarily Euclidean geometry type of problem that you will see in high schools. It's quite different. I mean, there are some very rare instances that you will see something on Euclidean geometry, but they are typically not that type. You do need to have some understanding of Euclidean geometry for some of these problems, but in general, they are not high school geometry type of problem. Okay, so the question is, you have a set of more than 2 to the power of n plus 1 over n distinct points with coordinates of the form plus minus 1, plus minus 1, plus minus 1. So all of the coordinates are plus minus 1 in the n-dimensional space with n greater than or equal to 3. We want to show that there are 3 distinct points in B that form an equilateral triangle. So interesting problem. Unfortunately, we can't really test a lot of small cases because the dimension is starting from 3. So if the problem were starting from n equals 1 or 2, that would make it a little bit easier for us to at least check more small cases. But given that it is n is at least 3, we would have 8 points here, plus minus 1, plus minus 1, plus minus 1. So these are 8 points, which, as you know, these 8 points are going to give us a cube. So you'll have cubes. You'll have 1 cube, and you are trying to kind of come up with equilateral triangles. So I do see that if I want to create equilateral triangles, the length of segments that I have here are either length 1, which are the edges of the cube, or length root 2, which are the diagonals of the faces, or I'm just going to assume that all of the edges of length 1. Or diagonals of the cube, which are of length root 3. So they have like 3 choices of length. And I can see that I can easily create equilateral triangles if I'm looking at length root 3. For example, this is one equilateral triangle here. If I connect these 3 points, so I'll get an equilateral triangle here. Okay, if I can draw that. Okay, so I get one equilateral triangle here. And then I get more equilateral triangles on this side. I get one. And then I get things on this side. I get another equilateral triangle. So I have 3 equilateral triangles right here. And then I can get another 3. So using these 4 points, I get 3 equilateral triangles. And then the other 4 more points exist that you can create another 3 equilateral triangles. So I won't draw that one, but they are going to use these 4 points. This point, this point, this point, and that point. Those 4 points are going to give you another 3 equilateral triangles. So overall, we have 6 equilateral triangles. And from these 6 equilateral triangles, I can choose every vertex. I can choose at most 2 of the vertices of each one of them. So that means I will be choosing 2 times 6 vertices. If I choose 2 of each, then I'm not going to get any equilateral triangle. But every vertex that I choose is going to be appearing 3 times, because every one of these vertices, so if you look at this vertex right here, it appears in 3 equilateral triangles. One, the red one, the green one, and the blue one. So there are, oh, actually this is 4 equilateral triangles, not 3. So there's one also in the back. So in total, I have 8 equilateral triangles. So if I choose 2 vertices from each one of them, I get 16 equilateral triangles. I'm sorry, 16 points, but then each point has been counted 3 times. So I can choose at most this many points without creating, so we may be able to choose this many points, 2 times 8 divided by 3. So we may be able to select 2 times 8 over 3. So again, 2 is 2 points per triangle. 8 is the number of triangles, and divided by 3. Why? Because every point is going to be counted 3 times in each of the equilateral triangles. So we may be able to select at most these many points without creating an equilateral triangle. Okay, so that is interesting because that's exactly the number that they gave us. That's the 2 to the power of n plus 1 over n, because n here is 3. Okay, so this makes me very happy because I got the exact same number that they gave me. So now the question is, how can I turn this into a proof that works for in general? Okay, so if I think about this one, I will see that I'm going to be able to create length root 2 triangles, length root 2 segments, if I have 2 length 1 segments. So if I have 2 length 1, then the hypotenuse becomes of length root 2. So I'm going to see how I'm able to create that type of thing. So looking back here, I'll see that each one of those is root 2, and they are created by looking at vertices. So if you look at these 3, for example, these 3 are all adjacent to this vertex right here. And because of that, you have a 1, 1, and then that would be root 2. And again, I'm assuming that the side length of the cube is 1, which in reality, you may have to assume it's root 2 because of the plus minus 1, plus minus 1. So in other words, if I get the neighbors of one of the points, if I get the points, the ones that I highlighted in yellow, that are all neighbors of the one that is in gray here, they all have distance root 2, which means from those 3 points, you cannot choose more than 2 points. And then I can use the same idea here. So I seem to be able to actually kind of repeat this argument. So if I'm starting from something like this, if I start from 1, 1, 1, then I can look at all of the neighbors of this. Neighbors means the one that have exactly one different coordinate. So negative 1, 1, 1, 1, 1, negative 1, 1, 1, 1, and all the way to 1, 1, 1, negative 1. So these are n points. Each one of them has a distance of root 2 with the other one. So that's kind of clear. If you take the first one and second one, the distance between those two is root. In fact, it's 2 root 2. But point is that they all have the same distance. So distance between these two is negative 1 minus 1 squared plus 1 minus negative 1 squared, and the rest is 0. So that's exactly 2 root 2. So from these n points, I can choose exactly 2 of them, not more than 2. You can choose 1 of them, but you cannot choose more than 2 of them. So I'll divide my vertices into these sets. Unfortunately, 2 to the power of n is not divisible by n. So you can't like you can't really divide 2 to the power of n vertices into exactly sets of this size. So there's going to be some left over. But what you can do is you could just ignore the repetition and then divide the vertices into these with some repetitions, and then see how many times each vertex is chosen, and then kind of repeat the same argument here. If something has been chosen like 3 times, and you divide everything by 3. Okay, so that seems to be a very reasonable approach. It's really the exact same idea that we used for n equals 3. So here's what we're going to do now. So for every A1 AN with AI equals plus minus 1, so I'm going to kind of call the neighbors of that. Neighbors of A1 through AN be the set of all negative A1, A2, all the way to AN, all the way to A1, AN minus 1, and negative AN. So now, note that each element of the neighbors of A1 through AN and A1 through AN are different at precisely 1 coordinate. So given that, that means the distance between each 2 points of the neighbors of A1 through AN is 2 square root of 2, because they only differ at 2 points, and then the difference would be 2 at that point, and then you square those, and then that gives you 2 root 2. Okay, so suppose on the contrary, no equilateral triangle exists in the selected points. Okay, thus from each neighbors of A1 through AN, we can select at most 2 points. So at most 2 points can be selected from each one of them, because if you select 3, then that's an equilateral triangle. Okay. Thus, so 2 times 2 to the power of n points are selected. Or I would have to say at most, because you may not select 2, you may select less than 2 from one of them. So I would have to say at most 2 times that number of points are selected. However, each point is selected. However, each point B1 through Bn is in precisely n neighbors of A1 through AN. Note that B1 through Bn is inside neighbors of A1 through AN if and only if, so these are neighbors if and only if A1 through AN is a neighbor of B1 through Bn. Because the way we defined the being neighbor was that they differ in exactly one coordinate, one component. So each point B1 through Bn is in precisely n of the neighbors. Thus, we cannot select more than, so we'll take the number 2 times 2 to the power of n divided by n points. And this is a contradiction. And this completes our proof.